Hello there, and welcome to the Sleepy Scholar. I'm so glad you found your way here. Perhaps you've had a long day, or maybe you're simply someone who finds comfort in the slow, patient rhythms of the natural world, in stories that unfold across millions of years rather than minutes or hours. Either way, tonight's journey is for you. You have nothing to do but rest. Let your breathing slow, your thoughts drift, and your body settle into the quiet knowledge that the earth beneath you has been moving, changing, and breathing for longer than the human mind can easily grasp. Because tonight, we're not rushing anywhere. We're sinking into geological time, into the deep patience of rock and mineral, into processes so gradual that entire mountains rise and fall between one moment and the next on the planet's timeline. We'll explore the layers beneath your feet, the slow dance of continents, the birth of crystals in darkness, and the gentle wearing away of stone by water and wind. Some of what you hear tonight might surprise you. Much of it will simply be peaceful. And just before we begin, if these calm, curious explorations help you unwind or give you a quiet way to end your day, consider liking and subscribing to the channel. It helps others find their way here too, one sleepy soul at a time. Let's begin slowly, gently, at the pace of stone. There is a kind of time that exists beyond human experience, a time so vast that our calendars and clocks become meaningless whispers. Geologists call it deep time, and it stretches back 4.54 billion years to the formation of Earth itself. That number, 4.54 billion, is difficult for the human brain to comprehend. We evolved to understand seasons, days, the span of a human lifetime. We can imagine 100 years, perhaps even 1,000, but billions. The scale becomes abstract, dreamlike, beyond the reach of intuition. And yet, this is the canvas on which Earth's story is painted. Every mountain, every ocean, every grain of sand carries within it a history that reaches back across unimaginable expanses of time. To help us understand deep time, imagine compressing all of Earth's history into a single calendar year. In this calendar, Earth forms on January 1st, just after midnight. For the first several months, the planet is a molten, inhospitable ball of rock and metal, slowly cooling under a young sun. The first simple life, single-celled organisms don't appear until around March. For most of the year, life remains microscopic, invisible to the naked eye, quietly building the foundations for everything that would come later. The first complex animals, creatures with hard shells and many cells, don't show up until mid-November. Dinosaurs appear around December 13th. They rule for about 9 days in our compressed calendar, then vanish suddenly on December the 26th. The entire age of mammals, everything from tiny shrew-like creatures to woolly mammoths to blue whales, occupies just the last few days of December. And humans, modern humans, people just like you and me, appear at around 11:52 p.m. on December 31st. All of recorded human history, everything from the first cities to the present day, takes place in the last minute before midnight. A single human lifetime is a fraction of a second. This is deep time. This is the patient, unhurried pulse of the planet. The geologic timescale is how scientists organize this immense span. It divides Bethesda into eons, the largest divisions. There are 4 formally recognized eons, though the earliest, the Hadean, is sometimes considered informal because we have almost no rock record from that period. The Hadean Eon, named after Hades, the Greek underworld, lasted from Earth's formation 4.6 billion years ago until about 4 billion years ago. During this time, the planet was still forming, still being bombarded by asteroids and comets, still too hot and chaotic for life as we know it. The Moon likely formed during the Hadean, when a Mars-sized object collided with the young Earth, sending debris into orbit that eventually coalesced into our lunar companion. The Archean Eon followed, from 4 billion to 2.5 billion years ago. The name comes from the Greek word for ancient, and it's during this time that the first continents began to form and the first life appeared. These early organisms were simple, single-celled creatures, but they would fundamentally change the planet. Some of them learned to photosynthesize, producing oxygen as a waste product. Over hundreds of millions of years, this oxygen would accumulate in the atmosphere, making Earth habitable for more complex life. The Proterozoic Eon, from 2.5 billion to 541 million years ago, saw the continued rise of oxygen and the eventual appearance of more complex multicellular life. For most of this eon, Earth was a strange place, sometimes covered almost entirely in ice in periods called snowball Earth events. Life persisted through these frozen epochs, waiting for the climate to change again. And then, 541 million years ago, everything changed. The Phanerozoic Eon began, and with it came an explosion of complex life. This is the eon we still live in today. Its name means visible life, and it's subdivided into 3 eras: the Paleozoic, Mesozoic, and Cenozoic. Ancient life, middle life, and recent life. Each era is further divided into periods, and periods into epochs, each one marked by the significant changes in the rock record or the fossil record. The boundaries between these divisions often correspond to major events: massive volcanic eruptions, asteroid impacts, dramatic climate shifts, the appearance or disappearance of important groups of organisms. But here's what's important to understand about the geologic timescale. These divisions aren't equal. Unlike the hours in a day or the months in a year, geological periods vary wildly in length. Some lasted hundreds of millions of years, others mere millions. The scale itself reflects the uneven, unpredictable rhythm of Earth's history, shaped by forces beyond anyone's control. Deep time invites us to see our place differently. We are not the culmination of Earth's history. We are a recent arrival, temporary inhabitants of a planet that has seen countless other inhabitants come and go. Mountains that seem eternal to us are merely young wrinkles on the face of a planet that has seen ranges rise and erode away dozens of times. The Atlantic Ocean, which seems like a permanent feature of geography, is actually quite young. It began forming only about 200 million years ago when the supercontinent Pangaea started to break apart. Before that, there was no Atlantic. Africa and South America were pressed together, their coastlines fitting like puzzle pieces, and the Atlantic is still growing. Every year it widens by a few centimeters as the ocean floor spreads at the mid-Atlantic ridge. Iceland, sitting astride that ridge, is quite literally being pulled apart, growing wider as the 2 plates beneath it move in opposite directions. In the grand scale of deep time, even oceans are temporary. They open and close like slow, patient mouths across hundreds of millions of years. Understanding deep time changes how we see erosion, sedimentation, the carving of canyons, the building of mountains. Processes that seem impossibly slow on human timescales become powerful forces capable of reshaping entire continents when given enough time. The Grand Canyon, one of Earth's most spectacular geological features, was carved by the Colorado River over approximately 6 million years. 6 million years of water flowing, carrying sand and silt, gradually cutting deeper and deeper into ancient rock layers. Each layer of rock in the canyon walls tells a story. Some layers formed in ancient seas, others in deserts, still others in river deltas. The deepest, oldest rocks at the bottom of the canyon are nearly 2 billion years old. Think about that. You can stand at the rim and look down through almost half of Earth's history. The rocks at the bottom were already ancient when the first animals were just beginning to appear in Earth's oceans. To truly grasp deep time, we need to find ways to make it tangible. One helpful comparison is to think of geological time in terms of a 24-hour clock. If all of Earth's 4.54 billion year history were compressed into a single day starting at midnight, the first signs of life wouldn't appear until around 4 a.m. Complex multicellular life doesn't show up until 8:40 p.m. Dinosaurs appear at 10:56 p.m. and go extinct at 11:39 p.m. Modern humans appear at 11:58:43 p.m., just 77 seconds before midnight. All of recorded human history, from the first written records to today, occurs in the last 0.2 seconds. This compression helps us understand just how recent we are in the grand sweep of Earth's history. We often think of ourselves as the main characters in Earth's story, but we're actually very late arrivals. For most of Earth's existence, there were no humans, no mammals, no dinosaurs, not even any animals, just single-celled organisms, slowly but steadily changing the planet, setting the stage for everything that would come later. Another way to visualize deep time is through the concept of human generations. A human generation is typically considered to be about 25 to 30 years. In 1,000 years, there are about 35 to 40 generations. To go back 1 million years, we'd need to count about 35,000 generations to reach the age of the dinosaurs. 65 to 230 million years ago, we'd need between 2.3 million and 8 million generations. To go back to Earth's formation would require counting over 150 million human generations. These numbers are so large that they become abstract. Our brains aren't wired to comprehend such spans, but that's precisely what makes deep time so humbling and, in a way, so calming. It puts everything in perspective. The problems that seem overwhelming on human timescales are momentary blips on geological timescales. The landscapes that seem permanent are actively changing, just too slowly for us to perceive. Earth has seen so much. It has been a snowball planet, covered almost entirely in ice. It has been a greenhouse planet, with tropical forests growing in what is now Antarctica. It has seen continents come together and break apart multiple times. It has witnessed the rise and fall of countless species, the building and erosion of countless mountain ranges, the opening and closing of oceans. And through all of this, through all these changes, the fundamental processes have remained the same. Gravity pulls things downward, heat flows from hot to cold, water cycles from ocean to cloud to rain to river, and back to ocean. Rock forms, transforms, and forms again. These are the constants, the underlying rhythms that have shaped Earth for billions of years. The same atoms have been recycled again and again. The oxygen you breathe was once part of a dinosaur. The carbon in your body was once dissolved in an ancient ocean. The hydrogen in your cells has been cycling through Earth's water system for billions of years. The iron in your blood was forged in a star that exploded billions of years before Earth formed, scattering its enriched material into space, where it eventually became part of the nebula that condensed to form our solar system. You are made of stardust and earth, of atoms that have been through countless transformations, that have been part of rock and water and air and living things before becoming part of you. When you die, those atoms will be recycled again, returning to Earth to become part of new rocks, new oceans, new life. Nothing is lost. Everything is transformed. This is the fundamental message of deep time and the rock cycle. This is the gift of geology. It gives us a window into deep time, a way to read Earth's history written in layers of stone. Every mountain range, every volcanic island, every grain of sand on a beach is a page in this vast book, if only we learn to read it. And here's something calming about deep time. It reminds us that change, even dramatic change, takes time. Mountains don't appear overnight. Continents don't split apart in an instant. Even the most violent geological events, earthquakes, volcanic eruptions, are just brief punctuation marks in a much longer, slower story. The Earth moves at its own pace, following rhythms measured in millions of years. There is something deeply peaceful about this perspective, about understanding that we live on a planet that has been here for so long, that will continue long after we're gone, patiently turning through space, mountains rising and falling like slow breaths. Deep time teaches patience, it teaches perspective. It teaches that even stone, which seems so permanent, is merely temporary on long enough timescales. Everything flows, everything changes, everything is part of a larger cycle that has been repeating for billions of years. As you rest tonight, consider that the ground beneath you is ancient. The atoms in your body were forged in stars that died billions of years ago. The air you breathe contains molecules that dinosaurs breathed. The water in your cells has cycled through oceans and clouds and rivers countless times over the planet's long history. You are made of Earth, you are part of deep time, and tonight you can rest in that knowledge, knowing that the planet's slow, patient rhythms continue, whether you're awake or asleep, always moving, always changing, always here. Beneath your feet, beneath the soil and bedrock, beneath the familiar surface world, Earth is organized in layers like a slow-motion explosion frozen in time. Each layer has its own temperature, its own pressure, its own strange and beautiful properties. We live on the thinnest layer, the crust. A delicate shell that wraps around the planet like the skin of an apple. And yet even this thin shell is thicker than we can easily comprehend. Under the oceans, the crust averages only about 5 kilometers thick, roughly 3 miles. Under the continents it averages 30 kilometers, though beneath major mountain ranges like the Himalayas, the crust can extend down 70 kilometers or more. To us, used to measuring distances in feet and miles, 70 kilometers seems vast. But compared to Earth's total radius of about 6,371 kilometers, the crust is incredibly thin. If Earth were the size of an apple, the crust would be thinner than the apple's skin. Everything we know, everything we've ever touched or seen directly exists in this gossamer layer. There are 2 types of crust. Continental crust, which forms the land we live on, is composed primarily of granite and similar rocks rich in silicon and aluminum. It's relatively light, which is why continents stand high above the ocean floors. It's also quite old. Some continental rocks are more than 4 billion years old, nearly as old as Earth itself. Oceanic crust, by contrast, is young and dark, composed primarily of basalt. It forms at mid-ocean ridges where tectonic plates pull apart and magma wells up to fill the gap, creating new ocean floor. Because oceanic crust is constantly being created at mid-ocean ridges and destroyed at subduction zones where it sinks back into the mantle, the oldest oceanic crust is only about 200 million years old. In geological terms, it's perpetually young, constantly being recycled. The crust rests on the mantle, by far Earth's largest layer by volume. The mantle extends from the base of the crust down 2,900 kilometers to the outer core. It makes up about 84% of Earth's total volume and 67% of its mass. The mantle is not molten, despite what many people think. It's solid rock, but it's under such tremendous temperature and pressure that it can flow very slowly over geological time. Think of it like cold honey or taffy. On human timescales, it's solid, but over millions of years it flows like a thick, viscous fluid. The mantle is composed primarily of iron, magnesium and silicon, formed into minerals like olivine and pyroxene. Near the top, where temperatures are around 1,300 degrees Fahrenheit, the mantle is relatively cool. But deep down near the core, temperatures reach about 7,200 degrees Fahrenheit. This temperature difference drives convection in the mantle. Hot material near the core rises slowly toward the surface, cools as it rises, then sinks back down again. These convection currents are what drive plate tectonics, the movement of Earth's crustal plates. The plates are carried along on the top of the slowly moving mantle like cargo on a conveyor belt, drifting at speeds of a few centimeters per year. The upper part of the mantle just below the crust includes a particularly interesting layer called the asthenosphere. This layer, extending from about 80 to 200 kilometers below the surface, is partially molten, with tiny pockets of melted rock dispersed through otherwise solid material. This makes the asthenosphere weak and plastic compared to the layers above and below it. The asthenosphere is crucial for plate tectonics. It's the slippery layer that allows the rigid lithosphere, the crust plus the uppermost mantle stuck to its base, to slide around. Without the asthenosphere, the tectonic plates would be locked in place, unable to move. Earth would be a very different planet, probably with no earthquakes, no volcanoes, no mountain building, and quite possibly no life as we know it. Below the asthenosphere is the mesospheric mantle, also called the lower mantle. This region is more solid than the asthenosphere because even though it's hotter, it's also under much greater pressure, and pressure keeps materials from melting. The lower mantle extends down to about 2,900 kilometers below the surface, where it meets the outer core. At the very bottom of the mantle, just above the core, is a mysterious layer called the D-double prime layer. Scientists aren't entirely sure what causes this layer's unusual properties. Some think minerals are undergoing another transformation here due to extreme pressure and temperature. Others suggest there might be small pools of melted rock, or that subducted slabs of oceanic crust that have sunk all the way through the mantle are piling up at the boundary between mantle and core. The core itself is divided into two parts. The outer core, extending from 2,900 kilometers below the surface down to about 5,150 kilometers, is liquid. It's composed primarily of iron and nickel, along with some lighter elements like sulfur or oxygen. Despite temperatures that reach 7,200 to 9,000 degrees Fahrenheit, hot enough to melt rock, the outer core remains liquid because the pressure isn't quite high enough to solidify it. The liquid outer core is constantly churning, driven by heat escaping from the even hotter inner core below. This churning liquid iron generates electrical currents, which in turn create Earth's magnetic field. This magnetic field is what makes compasses work, what creates the auroras at the poles, and what shields Earth from the worst of the solar wind, the stream of charged particles constantly flowing from the sun. Without this magnetic field, solar radiation would gradually strip away Earth's atmosphere, making the surface inhospitable to life. Mars, which lacks a strong magnetic field, lost most of its atmosphere billions of years ago. Earth's liquid outer core, constantly in motion, is one of the reasons our planet remains habitable. The inner core, at the very center of Earth, is solid despite being even hotter than the outer core. Temperatures here reach 9,000 to 10,800 degrees Fahrenheit, about as hot as the surface of the Sun, but the pressure at Earth's center is enormous, about 3.6 million times atmospheric pressure at sea level. This pressure is so great that it keeps the iron and nickel from melting. The inner core is a solid ball of metal about 1,500 kilometers in diameter, roughly 3/4 the size of Earth's moon. It's incredibly dense, made almost entirely of iron with some nickel mixed in, and it's doing something strange. It's rotating slightly faster than the rest of the planet, overtaking Earth's rotation by about 1 degree every million years or so. Earth's magnetic field, generated by that churning outer core, is more than just a curiosity that makes compasses work. It's actually essential for life as we know it. The magnetic field extends far out into space, creating a protective bubble called the magnetosphere that shields Earth from the solar wind, a constant stream of charged particles flowing from the sun. Without this protection, the solar wind would gradually strip away Earth's atmosphere, molecule by molecule, year by year, over millions of years. We can see what happens to a planet without a strong magnetic field by looking at Mars. Mars once had a magnetic field, but it shut down billions of years ago when the planet's core cooled and stopped generating the currents needed to sustain it. Without the protection of a magnetic field, Mars gradually lost most of its atmosphere to the solar wind. Today, Mars's atmosphere is less than 1% as thick as Earth's, and the surface is bathed in radiation that would be harmful to most forms of life. Earth's magnetic field also creates one of nature's most beautiful displays, the auroras, also called the northern and southern lights. When charged particles from the solar wind manage to slip through weaknesses in the magnetosphere near the poles, they collide with molecules in the upper atmosphere. These collisions energize the molecules, causing them to emit light, creating shimmering curtains of green, red, and sometimes purple light that dance across the sky in the polar regions. The magnetic field isn't constant. It wanders, with the magnetic North Pole drifting across the Canadian Arctic at speeds of up to 50 kilometers per year. It also weakens and strengthens over time, and every few 100,000 years on average, something remarkable happens. The field completely reverses, with magnetic north and south switching places. These reversals have happened hundreds of times in Earth's history. We know this because volcanic rocks preserved the direction of the magnetic field at the time they cooled, creating a record of past reversals. The mechanism behind these reversals is not fully understood, but it seems to be related to changes in the flow patterns of the liquid iron in the outer core. The reversals don't happen suddenly. Instead, they occur over a period of thousands of years, during which time the magnetic field weakens, becomes chaotic with multiple poles, and then reorganizes with reverse polarity. We're actually overdue for a reversal in the sense that it's been about 780,000 years since the last one, and reversals typically happen every 200,000 to 300,000 years. However, geological processes aren't perfectly regular, so this doesn't necessarily mean a reversal is imminent. The field has been weakening gradually over the past 2,000 years, which some scientists interpret as a possible precursor to a reversal, but it could also just be normal variation. If a reversal were to happen during human civilization, it would cause some disruptions. GPS system, power grids, and communication satellites all depend on accurate knowledge of Earth's magnetic field. But it wouldn't be catastrophic. The atmosphere would still protect us from most radiation, and we'd have centuries to adapt our technology. The main effect would probably be seeing auroras at much lower latitudes than usual, as the magnetic field temporarily weakens and becomes disorganized. We know all this about Earth's interior, without ever having drilled deeper than about 12 kilometers, less than 0.2% of the way to the center. How do we know what lies beneath? The answer is seismic waves, vibrations that travel through Earth when earthquakes occur. Different types of seismic waves travel at different speeds through different materials, and some types of waves can't travel through liquids at all. By studying how seismic waves from earthquakes change as they pass through the planet, bouncing off boundaries between layers and bending as they pass through materials of different densities, scientists can map Earth's interior with remarkable precision. It's like using sound to create an image, similar to how ultrasound lets doctors see inside the human body. Each major earthquake sends waves rippling through the entire planet, and seismometers all over the world record their arrival. By analysing thousands of earthquakes over many decades, scientists have pieced together a detailed picture of Earth's internal structure. They have also used calculations of Earth's mass and density, measurements of its gravitational field, and observations of how the planet wobbles on its axis. They've studied samples of mantle rock brought to the surface by volcanoes and compared them with meteorites, which are thought to be made of similar material as Earth's interior, since both formed from the same primordial cloud of dust and gas. The picture that emerges is of a planet organised by density. The lightest materials, silicon and aluminum-rich rocks, rose to form the crust during Earth's early history when the planet was still partially molten. Denser materials, iron and nickel-rich rocks, sank toward the centre. The very densest material, iron and nickel metal, sank all the way to the core. This process, called planetary differentiation, happened early in Earth's history, within the first few 100 million years after the planet formed. It released enormous amounts of heat as gravitational potential energy was converted to thermal energy. This heat, combined with heat from radioactive decay of elements like uranium and thorium, is what keeps Earth's interior hot today. Billions of years after formation, Earth is still cooling very gradually, releasing heat that has been trapped inside since its formation. The heat flowing out through the surface is what drives plate tectonics, powers volcanoes, and creates the convection currents in the mantle and outer core. It's what makes Earth a dynamic, living planet rather than a cold, dead world like the Moon or Mars. As you lie here tonight, imagine the layers beneath you. Imagine the solid crust, the slowly flowing mantle, the churning liquid outer core, the solid inner core spinning at the centre. Imagine the heat, the pressure, the slow dance of material moving through deep time. You're resting on top of all this, separated from unimaginable heat and pressure by only a few kilometres of cool solid rock. The ground feels still, solid, permanent. But deep below, the planet is alive, moving, changing, following patterns that have repeated for billions of years. It's a comforting thought in a way. The Earth knows what it's doing. It has been organising itself, layering itself, moving heat from deep inside to the surface for longer than life has existed. And it will continue long after we're gone. Patient, methodical, following the laws of physics written into the fabric of reality itself. Rest well on your thin, cool layer. Rest well knowing that below you the planet is taking care of itself, as it always has. If you could watch Earth from space for a few 100 million years, fast forwarding through time, you would see something astonishing. The continents would be moving, sliding across the surface like slow rafts, colliding with each other, splitting apart, rotating, coming together again in new configurations. What seems solid and permanent is actually fluid on geological timescales. The ground beneath your feet is moving right now, drifting slowly but inexorably toward new positions, carrying you along for the ride. This movement is plate tectonics, and it's one of the most important concepts in all of geology. It explains earthquakes, volcanoes, mountain ranges, ocean basins, and the distribution of fossils and minerals around the world. It's the unifying theory that ties together countless observations into a single, elegant framework. The story of plate tectonics begins with a German meteorologist named Alfred Wegener. In 1912, Wegener proposed something radical. He suggested that Earth's continents had once been joined together in a single enormous landmass, which he called Pangaea, meaning all Earth in ancient Greek. Wegener wasn't the first person to notice that the continents look like they might fit together. Mapmakers had been commenting on the way South America and Africa seemed to match like puzzle pieces since the 1500s. But Wegener went further. He found evidence. He noticed that rock formations in South America matched rock formations in Africa, not just in age but in type and sequence. Mountain ranges on one side of the Atlantic seemed to line up with mountain ranges on the other side, as if they had once been a single range that was torn apart. Certain fossils appeared on continents that were now widely separated by oceans, including fossils of land-dwelling creatures that couldn't possibly have crossed thousands of miles of open water. The fossils were particularly compelling. Glossopteres, an extinct seed fern, appeared in rocks in South America, Africa, India, Antarctica and Australia. Continents now separated by vast oceans. Mesosaurus, a freshwater reptile, appeared in both Brazil and South Africa. Cynognathus and Lystrosaurus, land-dwelling reptiles, appeared on multiple continents that are now widely separated. How could these organisms have spread across oceans? Wegener's answer was simple. They didn't cross oceans. They lived when the continents were joined, and the continents later drifted apart, carrying the fossilized remains with them. Wegener also found evidence of past climates that didn't match present climates. He found signs of ancient glaciation, layers of rock deposited by ice sheets in places that are now tropical. He found coal deposits, which form in warm, wet, swampy environments in Antarctica. The simplest explanation was that these continents had been in different positions relative to the equator and poles. Wegener published his ideas in 1912, and they were met with fierce resistance from most geologists. The evidence seemed compelling, but there was a fatal weakness in the theory. Wegener couldn't explain how continents moved. What force could be strong enough to push enormous landmasses thousands of kilometers across Earth's surface? Wegener suggested that continents might plough through the ocean floor the way ships plough through water, or that the rotation of Earth might cause them to drift. But other scientists, quite correctly, pointed out that these mechanisms were physically impossible. Continental rock isn't strong enough to plough through ocean floor rock without shattering. And Earth's rotation doesn't produce forces nearly strong enough to move continents. Without a mechanism, most geologists rejected Wegener's theory. Some even ridiculed it. Wegener died in 1930 during an expedition to Greenland before his ideas gained acceptance. For decades, continental drift remained a fringe theory. Interesting, but unproven. Then in the 1950s and 1960s, everything changed. New technology developed during World War II, particularly sonar and magnetometers used to detect submarines, was turned towards studying the ocean floor, and what scientists found there revolutionized geology. They discovered that the ocean floors weren't flat, featureless plains. Running down the center of each major ocean was a massive underwater mountain range, tens of thousands of kilometers long. The mid-ocean ridges, as these ranges were called, were the longest continuous mountain chains on Earth, and they were volcanically active with magma welling up from below. Even more striking, the ocean floor on either side of these ridges showed a distinctive pattern. When volcanic rock cools, magnetic minerals within it align with Earth's magnetic field, recording the field's direction like tiny compasses. Earth's magnetic field reverses periodically, roughly every 200,000 to 300,000 years, with the north and south magnetic poles switching places. Ocean floor rocks recorded these reversals in parallel stripes, with rocks of alternating magnetic polarity stretching away from the mid-ocean ridges on both sides. The pattern was symmetric. The stripes matched on either side of the ridge like mirror images. There was only one explanation that made sense. New ocean floor was forming at the mid-ocean ridges, pushing older ocean floor away on both sides. As the new floor formed, it recorded the magnetic field direction at that time. As the field reversed, new rock with opposite polarity was created. Over millions of years, this process created the observed pattern. This was seafloor spreading, and it provided the mechanism that Wegener's theory had lacked. Continents weren't ploughing through the ocean floor, they were being carried along as new ocean floor formed and old ocean floor was destroyed. Scientists realized that Earth's surface was divided into about a dozen major plates and numerous smaller ones. These plates, composed of crust and the rigid uppermost mantle stuck to the bottom of the crust, float on the asthenosphere, the partially molten layer of the mantle below. The plates move because of convection currents in the mantle, driven by heat escaping from Earth's interior. Where plates pull apart and mid-ocean ridges, magma wells up to fill the gap, creating new crust. Where plates push together, several things can happen. If two oceanic plates collide, the older, denser, cooler plate sinks beneath the younger one in a process called subduction. The sinking plate is recycled back into the mantle, eventually to be melted and perhaps returned to the surface through volcanoes. If an oceanic plate collides with a continental plate, the denser oceanic plate sinks beneath the lighter continental plate, again through subduction. This creates deep ocean trenches, the deepest places on Earth, and it generates chains of volcanoes on the overriding continental plate as water and other materials released from the subducting plate rise into the mantle above, lowering its melting point and producing magma. The Andes Mountains, running along the western edge of South America, are a perfect example. They formed and continue to grow as the Nazca Plate, an oceanic plate in the Pacific, subducts beneath the South American plate. The volcanoes in the Andes are fed by magma generated in this subduction zone. If two continental plates collide, neither wants to sink because both are light and buoyant. Instead, they crumple, and the crust thickens, building mountains. The Himalayas, including Mount Everest, the highest point on Earth's surface, are forming because the Indian plate is colliding with the Eurasian plate. India was once a separate continent, far to the south, but it drifted northward and slammed into Asia about 50 million years ago. The collision is still ongoing. The Himalayas continue to rise as India continues to push north. Where plates slide past each other horizontally, they create transform boundaries. The San Andreas Fault in California is a transform boundary where the Pacific plate is sliding north relative to the North American plate. Los Angeles on the Pacific plate is slowly moving towards San Francisco on the North American plate at about 5 centimeters per year. In about 15 million years, they'll be neighbors. Plate tectonics explains so much. It explains why earthquakes and volcanoes are concentrated along plate boundaries, particularly around the Pacific Ocean in a region known as the Ring of Fire. It explains how mountain ranges form through continental collision or volcanic activity above subduction zones. It explains the youth of the ocean floors and the great age of the continents. It also explains the distribution of life. When Pangaea existed, about 300 million years ago, all land-dwelling life had access to the entire supercontinent. As Pangaea broke apart starting about 200 million years ago, populations were separated. They evolved in isolation, developing into different species. This is why Australia has such unique animals, marsupials like kangaroos and koalas. Australia separated from other continents about 45 million years ago and has been isolated ever since, allowing its fauna to evolve independently. The Atlantic Ocean, which now separates South America and Africa, began forming about 200 million years ago. It's still growing, widening by a few centimeters each year. The Pacific Ocean, by contrast, is shrinking as oceanic plates around its edges subduct beneath the continents. In a few 100 million years, the Pacific may close completely, and the continents may come together again to form a new supercontinent, just as Pangaea formed from the collision of earlier continents. This process, the opening and closing of ocean basins as continents split apart and come back together, is called the Wilson cycle, named after geophysicist J. Wilson, who described it. It's a fundamental rhythm of the planet, a cycle that repeats roughly every 400 to 600 million years. Pangaea was just the most recent supercontinent. Before Pangaea there was Pannonia, and before that Rodinia, and before that others whose names and configurations are still being worked out. Earth's surface is constantly being renewed, rearranged, recycled. The arrangement of continents and oceans that we see today is just a snapshot, a single frame in a very long movie. The map of Earth 100 million years from now will look very different. Africa is splitting apart along the East African Rift. Eventually, in perhaps 10 million years, the eastern part of Africa may break away entirely, creating a new ocean. The Mediterranean Sea is closing as Africa pushes northward toward Europe. In 50 million years or so, the Mediterranean may be gone, and a new mountain range, higher than the Alps, may stretch from Spain to Turkey. California, or at least the part west of the San Andreas Fault, is slowly detaching from North America and will eventually become an island, like New Zealand or Japan, drifting off into the Pacific. The continents are not permanent features. They are temporary arrangements, rafts of light rock floating on the denser mantle, drifting around the planet at the pace of fingernail growth, colliding, splitting, occasionally gathering together before dispersing again. And here's something calming about this. For all the immense forces involved, tectonic plates move very slowly, just a few centimeters per year. At this pace, you won't notice the motion in a lifetime, or a dozen lifetimes. The world feels solid and stable because on human timescales it is. But if you could watch through the lens of deep time, you would see Earth's surface in constant, graceful motion. Continents drifting like dancers across a stage, mountains rising and falling like slow breaths, oceans opening and closing like slow, patient mouths. Tonight, as you rest, the tectonic plate beneath you is moving. North America is drifting westward, away from Europe, widening the Atlantic Ocean by a few millimeters. The motion is imperceptible, but it's real. You are a passenger on a journey that began billions of years ago and will continue for billions more, carried along by forces you can't feel, but that shape the very ground you rest on. It's a quiet, patient motion. There's no hurry. The Earth has all the time in the world, and so tonight, do you. There is a kind of alchemy happening beneath your feet, a slow transformation of one type of rock into another, a cycle that has been repeating for billions of years. It's called the rock cycle, and it's how Earth recycles its crust, turning ocean floor into mountains, mountains into sand, sand into stone, and stone back into magma to begin again. Rocks are divided into three main types based on how they form: igneous, sedimentary, and metamorphic. But these aren't permanent categories. any rock can transform into any other type of rock given the right conditions and enough time. The rock cycle is the set of processes that make these transformations happen. Let's begin with igneous rocks, which form from the cooling and solidification of molten material. Deep within Earth, in the mantle and in areas where the crust is particularly hot, rock can melt, forming magma. This magma is lighter than the solid rock around it, so it rises, slowly working its way upward through cracks and weaknesses in the overlying rock. Sometimes magma reaches the surface, erupting from volcanoes as lava. This lava cools quickly in the relatively cold air or water, forming extrusive or volcanic igneous rocks. Basalt, the dark rock that forms most of the ocean floor, is an extrusive igneous rock. So is obsidian, volcanic glass that cools so quickly that mineral crystals don't have time to form. Pumice, the light, porous rock that can float on water, forms when lava with lots of gas bubbles cools quickly, trapping the bubbles inside. But not all magma reaches the surface. Much of it cools slowly underground, trapped in chambers or injected into cracks in existing rock. This magma cools slowly over thousands or even millions of years, allowing large crystals to grow. The resulting rocks are called intrusive or plutonic igneous rocks. Granite is the most familiar example, a coarse-grained rock with visible crystals of quartz, feldspar and mica. You can see granite in many buildings and countertops, its speckled appearance created by the interlocking crystals that grew as the magma cooled slowly underground. The size of the crystals tells you how fast the magma cooled. Large crystals mean slow cooling deep underground. Small crystals mean fast cooling near the surface. No crystals at all, as in obsidian, mean extremely rapid cooling. As magma cools, different minerals crystallize at different temperatures. The process is systematic, following what's called Bowen's reaction series. High-temperature minerals like olivine and calcium-rich plagioclase feldspar crystallize first when the magma is still very hot. As the magma continues to cool, minerals with progressively lower melting points crystallize, eventually ending with quartz and potassium-rich feldspar, which crystallize at the lowest temperatures. This sequential crystallization means that a single body of magma can produce different types of igneous rocks as it cools, and different minerals crystallize at different depths or times. It's a beautiful example of how chemistry and temperature work together to create the diversity of rocks we see. But igneous rocks don't remain unchanged forever. Once they're exposed to Earth's surface, or even before they reach the surface, they begin to weather. Weathering is the process by which rocks are broken down into smaller pieces by physical and chemical processes. Physical weathering includes frost wedging, where water seeps into cracks, freezes, expands, and splits the rock apart. It includes thermal expansion and contraction, where rocks heat up during the day and cool at night, eventually cracking from the repeated stress. It includes biological weathering, where plant roots grow into cracks and widen them, or where burrowing animals break up rock. Chemical weathering involves chemical reactions that change the minerals in the rock. Water, especially slightly acidic rainwater, can dissolve some minerals. Oxygen in the atmosphere can react with iron in rocks, forming iron oxides, the rust-coloured coating you see on many rock surfaces. Carbon dioxide dissolved in water forms carbonic acid, which can dissolve limestone and other carbonate rocks, creating caves and sinkholes. The products of weathering, fragments of rock ranging from boulders to sand to clay, are collectively called sediment. This sediment is then transported by water, wind, ice, or gravity to new locations where it accumulates, usually in layers. Over time, these layers of sediment are buried under newer layers. The weight of the overlying material compresses the sediment, squeezing out water and packing the grains more tightly together. Minerals dissolved in groundwater precipitate between the grains, cementing them together. Slowly, the loose sediment turns into solid rock. This process is called lithification. The rocks formed this way are sedimentary rocks, the second major category. Sandstone forms from lithified sand. Shale forms from lithified mud or clay. Conglomerate forms from lithified gravel. These are clastic sedimentary rocks. Rocks made from fragments of other rocks. But there are other kinds of sedimentary rocks too. Chemical sedimentary rocks form when minerals dissolved in water precipitate out of solution, usually because the water evaporates or because conditions change. Rock salt and gypsum form this way in shallow seas or salt lakes that periodically dry up. Organic or biological sedimentary rocks form from the accumulation of organic material. Coal forms from plant material that was buried in swamps before it could fully decay. Given enough heat and pressure over millions of years, the plant material is transformed into coal, a sedimentary rock that's essentially concentrated carbon. Limestone often forms from the shells and skeletons of marine organisms, made of calcium carbonate. When these organisms die, their shells accumulate on the seafloor, eventually lithifying into limestone. Sedimentary rocks are remarkable because they preserve Earth's history. The layers, or strata, form in sequence, with older layers on the bottom and younger layers on top. Each layer records the conditions that existed when it was deposited. A sandstone layer might indicate a desert or a beach. A limestone layer might indicate a shallow tropical sea. A coal layer indicates a swamp. A layer rich in fossils tells about the life that existed at that time. By studying the sequence of sedimentary rock layers, geologists can reconstruct Earth's history, determining which areas were underwater, which were above sea level, when climates changed, when life forms appeared or went extinct. Sedimentary rocks are the pages of Earth's history book, but the rock cycle doesn't end with sedimentary rocks. If sedimentary rocks, or igneous rocks, or even previously metamorphosed rocks, are subjected to enough heat and pressure, they can be transformed into metamorphic rocks, the third major category. Meta means change, and morph means form. Metamorphic rocks are rocks that have changed form. This transformation happens deep underground, where temperatures are high and overlying rocks create enormous pressure. The heat and the pressure cause the minerals in the rock to recrystallize, forming new minerals and new textures without the rock actually melting. If the rock melted, it would become magma, and when it solidified, it would be an igneous rock, not a metamorphic rock. Metamorphism happens in the solid state. Shale, a sedimentary rock made of clay minerals, can be transformed into slate with relatively low heat and pressure. With higher temperatures and pressures, slate can be transformed into phyllite, then schist, then gneiss. Each transformation involves recrystallization and the growth of larger mineral crystals. Gneiss, with its characteristic banded appearance of alternating light and dark minerals, is a high-grade metamorphic rock formed under intense heat and pressure. Limestone, made of calcium carbonate, can be transformed into marble, a metamorphic rock prized for sculpture and architecture. Sandstone can be transformed into quartzite, one of the hardest and most durable rocks. Metamorphic rocks often form in mountain ranges where tectonic forces have pushed rocks deep underground or where rocks have been in contact with hot magma. The Appalachian Mountains, for example, contain extensive areas of metamorphic rock, formed when this region was squeezed and heated during the collision of continents that formed the supercontinent Pangaea. And here's where the cycle completes. If metamorphic rocks are buried deep enough and get hot enough, they can melt, forming magma. This magma can then cool to form new igneous rocks, and the cycle begins again. Or, if the metamorphic rocks are uplifted and exposed at the surface, they can weather and erode, forming sediment that eventually lithifies into sedimentary rocks. Any rock can become any other type of rock through the right sequence of processes. Igneous rocks can weather into sediment that becomes sedimentary rocks. Sedimentary rocks can be heated and pressurized to become metamorphic rocks. Metamorphic rocks can melt to become igneous rocks. Igneous rocks can be metamorphosed without melting. Sedimentary rocks can be completely subducted and melted without ever being metamorphosed. The pathways through the rock cycle are numerous and complex, and throughout this cycle, minerals are forming. Minerals are naturally occurring inorganic crystalline substances with a definite chemical composition. They are the building blocks of rocks. Most rocks are made of 2 or more minerals mixed together. Minerals form whenever conditions are right for atoms to arrange themselves into ordered, repeating structures. In magma, minerals crystallize as the melt cools. In sedimentary environments, minerals can precipitate from water. During metamorphism, new minerals form as atoms are rearranged into more stable configurations for the new temperature and pressure conditions. The crystal structure, the 3-dimensional arrangement of atoms in a mineral, determines many of the mineral's properties, its hardness, its cleavage, the way it breaks along certain planes, its colour, its luster. Quartz, for example, is made of silicon and oxygen arranged in a framework structure. This makes it very hard and resistant to weathering. Micas have sheet structures, with strong bonds within sheets, but weak bonds between sheets, which is why they split so easily into thin, flexible layers. Some minerals form gemstones. Diamonds are pure carbon, with each carbon atom bonded to 4 others in an extremely strong 3-dimensional network. This structure makes diamond the hardest naturally occurring substance. Diamonds form deep in the mantle where pressures are high enough to squeeze carbon atoms into this configuration. They are brought to the surface in volcanic eruptions carried in magma that rises rapidly from depths of 150 kilometers or more. Sapphires and rubies are varieties of the mineral corundum, aluminum oxide. Pure corundum is colorless, but tiny amounts of other elements create vivid colors. A trace of chromium makes corundum red, a ruby. Traces of iron and titanium make it blue, a sapphire. Other trace elements create yellow, pink, or green sapphires. Emeralds are varieties of the mineral beryl, coloured green by trace amounts of chromium or vanadium. Amethyst is purple quartz coloured by traces of iron. These gemstones form under specific conditions in specific environments. Finding them requires understanding where and how they form. Another way geology connects us to the beauty hidden within Earth's depths. The rock cycle is one of the most fundamental concepts in geology because it shows that rocks are not static. They're constantly changing, transforming from one type to another, being recycled through Earth's crust and mantle. The granite that makes up a mountain today might once have been basalt on the ocean floor, then subducted, melted, and reborn as granite. Millions of years from now, that granite might be weathered into sand, lithified into sandstone, metamorphosed into quartzite, subducted and melted again, erupting from a volcano as basalt, beginning another cycle. Nothing is permanent. Everything flows, everything changes, everything is part of a larger system that's been operating for billions of years. The atoms in the rocks beneath you have been through this cycle many times. They've been deep in the mantle, erupted from volcanoes, weathered and washed into ancient seas, buried, heated, uplifted, eroded, and buried again. Each grain of sand on a beach has a long, complex history, if only we could read it. Tonight, as you rest, imagine this slow cycle. Imagine rock being born from magma, weathered by water and wind, buried under newer layers, transformed by heat and pressure, perhaps melted and born again. Imagine the patient, unhurried way that Earth reshapes itself, grinding old rocks into new ones, breaking things down and building them up again. It's a cycle without beginning or end, a perpetual transformation that will continue as long as Earth has internal heat to drive it. There is something calming about this cyclical view, the knowledge that nothing is lost, only transformed, that the materials of Earth's crust are endlessly recycled, always changing form but never disappearing. Rest in this knowledge, rest knowing that the solid rock beneath you is part of this ancient ongoing cycle, slowly changing, slowly moving through its long journey from one form to another and back again. There are places on Earth where the interior reaches the surface, where molten rock from deep below breaks through the crust and flows out into the air or ocean. These are volcanoes, and they are windows into Earth's depths, reminders that beneath the cool solid surface lies unimaginable heat. Volcanoes occur where magma, molten rock from the mantle or deep crust, finds a path to the surface. There are about 1,500 active volcanoes on Earth, meaning volcanoes that have erupted in recorded history and could erupt again. Most of them lie along tectonic plate boundaries, particularly around the Pacific Ocean in the Ring of Fire, a horseshoe-shaped belt where oceanic plates subduct beneath continental or other oceanic plates. Subduction zones are where most volcanoes form. As an oceanic plate sinks into the mantle, it carries with it water, trapped in minerals and sediments. This water is released at depth, rising into the hot mantle above the subducting plate. Water lowers the melting point of rock, causing the mantle to partially melt. The resulting magma, being less dense than the surrounding rock, rises slowly toward the surface. Much of this magma solidifies underground, but some reaches the surface erupting as lava. The Cascade Range in the Pacific Northwest, including famous volcanoes like Mount St. Helens and Mount Rainier, formed this way above the subduction zone where the Juan de Fuca plate sinks beneath North America. The Andes Mountains in South America formed the same way, above the subduction of the Nazca plate. But not all volcanoes are at plate boundaries. Some, like the volcanoes of Hawaii, form in the middle of plates, above hot spots, plumes of unusually hot rock rising from deep in the mantle. These plumes remain relatively stationary while the tectonic plate above them moves. As the plate drifts over the hot spot, a chain of volcanoes forms, with the oldest volcanoes farthest from the hot spot and the youngest directly above it. The Hawaiian Islands are a perfect example. The Big Island of Hawaii, where the volcanoes Kilauea and Mauna Loa are active, sits above the hot spot. To the northwest are older islands, progressively more eroded and extinct. Eventually the Big Island will drift off the hot spot, its volcanoes will go extinct, and a new island will form to the southeast, already building on the seafloor as Loihi Seamount, the newest volcano in the chain. Magma composition determines how a volcano erupts. Magma rich in silica, the chemical compound silicon dioxide, is thick and viscous, like cold honey or taffy. Gases dissolved in this magma can't easily escape. As the magma rises and pressure decreases, gases come out of solution, forming bubbles. If the magma is too viscous for the bubbles to escape, pressure builds until the volcano erupts explosively, blasting ash, rock fragments, and gases high into the atmosphere. These explosive eruptions are dangerous. They can produce pyroclastic flows, avalanches of hot gas, ash, and rock fragments that race down the volcano's slopes at speeds up to 700 kilometers per hour, incinerating everything in their path. The 1902 eruption of Mount Play in Martinique produced a pyroclastic flow that destroyed the city of Saint-Pierre, killing nearly 30,000 people in minutes. The 1980 eruption of Mount St. Helens produced pyroclastic flows that devastated hundreds of square kilometers of forest. Magma low in silica, like the basaltic magma that forms oceanic crust, is thin and runny. Gases can escape easily, so eruptions are typically gentler, with lava flowing rather than exploding. Hawaiian volcanoes are known for these effusive eruptions where lava flows steadily from vents, sometimes forming spectacular lava fountains but rarely exploding violently. These flowing basaltic lavas can travel long distances before solidifying. In Hawaii, lava flows have been known to reach the ocean, several kilometers from the vent, creating new land as the lava cools and hardens. Basaltic lava can move surprisingly fast in lava tubes, insulated channels where the surface of the flow has solidified, but molten lava continues to flow beneath. But usually lava moves slowly enough that people can walk ahead of it. Lava that flows out of a volcano and cools on the surface forms different textures depending on how it cools and how much gas it contained. Peihoehui is smooth, ropey lava that forms when fluid happens. Basaltic lava flows gently and cools slowly enough for a smooth skin to form. The skin wrinkles and folds as the still molten lava beneath continues to flow, creating characteristic rope-like textures. Aa is rough, jagged lava that forms when viscous basaltic lava moves more slowly and its surface breaks up into sharp, angular fragments. Walking on Aa lava is difficult. Its sharp edges can cut through shoes and the surface is unstable, with loose fragments that shift underfoot. Pillow lava forms when basaltic lava erupts underwater. The outer surface cools instantly on contact with water, forming a glassy skin, while the interior remains molten. As more lava is extruded, it breaks through the skin, forming new pillows. The result is a pile of elongated pillow-shaped structures, each with a glassy outer rind and a more crystalline interior. Much of the ocean floor is covered with pillow basalts, evidence of underwater volcanic activity along the mid-ocean ridges. Volcanic eruptions also produce tephra, any solid material ejected into the air. This includes volcanic bombs, large chunks of molten or semi-solid lava thrown through the air, which cool and solidify before landing. It includes pumice, light, porous rock full of gas bubbles, which forms when gas-rich lava is blasted apart and the fragments cool rapidly in the air. Pumice is so light and full of holes that it can float on water. Volcanic ash, despite its name, isn't burned material. It's tiny fragments of volcanic glass and rock less than 2 millimeters across, formed when explosive eruptions shatter magma into fine particles. Volcanic ash can be carried by winds for thousands of kilometers, circling the globe. Major eruptions can inject ash high into the stratosphere, where it can remain for months or years, reflecting sunlight and cooling global temperatures. The 1815 eruption of Mount Tambora in Indonesia was the largest volcanic eruption in recorded history. It ejected so much ash into the atmosphere that it caused the year without a summer in 1816. Crops failed across the northern hemisphere due to unseasonably cold weather, leading to widespread famine. The effects of a single massive eruption reached around the world. Volcanoes also release gases. The most common volcanic gas is water vapor, followed by carbon dioxide and sulfur dioxide. These gases can be hazardous. Sulfur dioxide reacts with water in the atmosphere to form sulfuric acid, which falls as acid rain. Carbon dioxide, being denser than air, can accumulate in low-lying areas, displacing oxygen and suffocating people and animals. In 1986, a sudden release of carbon dioxide from Lake Nyos in Cameroon killed more than 1,700 people and thousands of animals. But volcanoes aren't only destructive, they're also creative, one of the primary ways that new crust forms, and that material from Earth's interior reaches the surface. Volcanic eruptions have released most of the water vapour that formed Earth's oceans, and much of the atmosphere minus oxygen. Volcanic rocks weather into rich, fertile soils. Many of the most productive agricultural regions in the world are on volcanic soil, the slopes of dormant volcanoes, because volcanic rock weathers into soil rich in nutrients. Volcanic islands, formed by repeated eruptions building up from the ocean floor, provide new habitat for life. Hawaii is entirely volcanic, built up over millions of years by countless eruptions. Iceland sits astride the mid-Atlantic ridge, growing wider as new volcanic rock forms along the spreading centre that runs through its middle. Not all volcanoes are mountains. Some are immense, gently sloping shields, like Mauna Loa in Hawaii, which rises more than 9 kilometers from the seafloor to its summit, making it the world's largest volcano by volume. Its gentle slopes, averaging only about 5 degrees, are formed by countless basaltic lava flows spread out over a wide area. Some volcanoes are steep-sided stratovolcanoes or composite volcanoes, formed by alternating layers of lava flows and pyroclastic material. Mount Fuji in Japan, Mount Rainier in Washington, and Mount Vesuvius in Italy are stratovolcanoes. These tend to be the most dangerous because they're prone to explosive eruptions. Some volcanic activity produces lava domes, thick steep-sided mounds of viscous lava that pile up around a vent, because the lava is too thick to flow away. Lava domes can grow rapidly and then collapse catastrophically, producing pyroclastic flows. Calderas are large basin-shaped depressions that form when the ground collapses following a massive eruption that empties the magma chamber beneath a volcano. Crater Lake in Oregon formed this way about 7,700 years ago, when Mount Mazama erupted and then collapsed. The resulting caldera, about 8 kilometers across, later filled with rain and snowmelt to form the lake. Yellowstone National Park sits within a massive caldera, about 55 by 72 kilometers, formed by an enormous eruption about 640,000 years ago. The entire park is an active volcanic system, though it hasn't erupted in recorded history. The hot springs, geysers, and other geothermal features are powered by the magma chamber still present at depth. As you rest tonight, consider that beneath the seemingly solid ground, Earth is hot and restless. Magma chambers sit hidden kilometers below the surface, molten rock waiting for the chance to rise. In some places, this magma finds its way to the surface, building new land, releasing gases, reshaping the landscape. The volcanoes that erupt today are temporary features, but the process continues. As long as Earth has internal heat, as long as the mantle convects and plates move, there will be volcanoes. They're part of the planet's ongoing cycle, one of the ways Earth releases internal heat and renews its surface. There's something almost peaceful about lava flows, despite their heat and danger. They move slowly, deliberately, unstoppable but not sudden. They follow paths of least resistance, flowing around obstacles, filling depressions, covering everything in their path with fresh new rock. When they cool and solidify, they add to the land, building up coastlines, creating new islands, filling valleys. Lava, in a way, is Earth's blood. It flows from deep within, carrying heat and material from the interior to the surface, then cools and solidifies into new crust. It's part of the planet's circulation system, a way that Earth exchanges material between its different layers. Rest well, knowing that these volcanic processes, dramatic as they seem, are just Earth doing what it has always done, releasing heat, recycling material, reshaping its surface in a cycle that has repeated for billions of years and will continue for billions more. The planet knows its work, and it does it patiently, following the laws of chemistry and physics, building and breaking, melting and solidifying in an endless slow dance. Nothing lasts forever, not even rock. Given enough time, even the mightiest mountains crumble into sand. Water and wind, heat and cold, plants and chemistry all work together to break down rock into smaller and smaller pieces. This is weathering and erosion, the slow dismantling of Earth's solid surface. Weathering is the breakdown of rock in place, at or near the surface. It doesn't involve transporting the broken material away. Erosion is the removal and transportation of weathered material by water, wind, ice, or gravity. Together, these processes have been reshaping Earth's surface for as long as land has existed above sea level. Physical weathering, also called mechanical weathering, breaks rock into smaller pieces without changing its chemical composition. One of the most effective forms of physical weathering is frost wedging. Water seeps into cracks in rock. When the temperature drops below freezing, the water turns to ice. Ice occupies about 9% more volume than the same amount of liquid water, so it expands with tremendous force, widening the crack. When the ice melts, water can penetrate deeper into the widened crack. The cycle repeats, each freeze-thaw cycle wedging the crack wider until eventually the rock splits apart. This process is particularly effective in climates with frequent freeze-thaw cycles, like mountains and high latitudes. It's one reason why mountainous regions have so much broken rock, talus slopes of angular fragments that have been pried off cliff faces by frost action. Another form of physical weathering is thermal expansion and contraction. Rock expands slightly when heated and contracts when cooled. Daily temperature changes, especially in deserts where days are hot and nights are cold, cause the surface of rock to expand and contract repeatedly. Over time, this stress can cause the surface layers to flake off in a process called exfoliation or sheeting. Pressure release can also break up rock. Rock that forms deep underground is under enormous pressure from the weight of overlying material. If this rock is uplifted and the overlying material is eroded away, the pressure decreases rapidly. The rock expands slightly, and expansion can cause cracks to form parallel to the surface. Large sheets of rock can spall off like layers of an onion being peeled away. This creates rounded, dome-shaped landforms, like those in Yosemite National Park. Biological weathering occurs when living things break up rock. Plant roots grow into cracks in rock, widening them as the roots expand. Trees growing in cracks can eventually split large boulders apart. Burrowing animals, from earthworms to prairie dogs, bring rock fragments to the surface where they're more exposed to weathering. Lichens and mosses growing on rock surfaces produce weak acids that etch away at the minerals. Chemical weathering changes the chemical composition of minerals, often making them softer and more easily broken down. Water is a powerful agent of chemical weathering. Even pure water can dissolve some minerals, but most rainwater is slightly acidic, containing dissolved carbon dioxide that forms carbonic acid. This weak acid can dissolve calcite, the mineral that makes up limestone and marble. Over time, rainwater percolating through limestone can create caves, dissolving the rock and carrying away the dissolved material. Some of the largest cave systems in the world, like Mammoth Cave in Kentucky and Carlsbad Caverns in New Mexico, formed through chemical weathering of limestone. The caverns are decorated with stalactites hanging from the ceiling and stalagmites rising from the floor, formed when dissolved calcite precipitates out of dripping water, building up tiny crystal layers over thousands of years. Oxidation is another form of chemical weathering. When minerals containing iron are exposed to oxygen and water, the iron oxidizes, forming iron oxide, better known as rust. This is why many rocks have reddish or brownish stains or coatings. Iron oxide is softer and more easily broken down than the original iron-bearing minerals, so oxidation weakens rock and makes it more susceptible to physical weathering. Feldspar, one of the most common minerals in granite and many other rocks, is susceptible to hydrolysis, a chemical weathering process where water reacts with the mineral to form clay minerals. Granite weathering is slow, but over millions of years, feldspars in granite transform into klacitskul, which is soft and easily eroded. The quartz in granite is much more resistant to chemical weathering, so it remains as sand grains when the clay is washed away. Much of the sand on beaches comes from weathered granite. Once rock has been weathered into smaller fragments, erosion can transport these fragments to new locations. Water is the most powerful agent of erosion on Earth. Rain splash erosion occurs when raindrops hit bare soil, dislodging particles that can then be carried away by flowing water. Sheet erosion occurs when water flows across the surface in a thin layer, carrying sediment with it. This is particularly effective on slopes and on agricultural land where the soil surface is exposed. Streams and rivers are extremely effective at erosion. Flowing water has energy, and this energy can move sediment. The faster the water flows, the more energy it has and the larger the particles it can move. Mountain streams with steep gradients can move boulders. Lowland rivers with gentle gradients move mainly sand and silt. Running water erodes rock in several ways. It can dissolve minerals directly, it can break off pieces of rock through hydraulic action, the sheer force of water hitting rock. But most erosion happens through abrasion, when sediment carried by the water grinds against the riverbed and banks like liquid sandpaper. Over millions of years, rivers can carve deep valleys and canyons through solid rock. The Grand Canyon, carved by the Colorado River, is the most spectacular example in North America. But every stream and river is cutting into the land, slowly lowering the surface. Wind is another agent of erosion, though it's generally less powerful than water. Wind can only move small particles, dust and sand. But in arid regions with little vegetation to hold the soil in place, wind erosion can be significant. Wind-carrying sand acts as a sandblaster, wearing away rock surfaces, especially softer rock layers, creating unusual shapes and features. Desert regions often show the effects of wind erosion, with rock formations carved into strange shapes, their bases worn away by wind-blown sand. Sand dunes are evidence of wind erosion and deposition, formed when wind-transported sand is deposited in areas where the wind slows down, often behind obstacles or in areas with vegetation. Ice is a powerful erosional agent. Glaciers, vast rivers of ice that flow slowly down valleys or spread across continents, can move not just sand and silt but huge boulders. As glaciers move, they pick up rock fragments from the valley floor and walls. These fragments, frozen into the bottom and sides of the glacier, grind against the bedrock as the glacier flows like a giant rasp. This glacial abrasion can polish bedrock to a smooth surface, or it can carve deep scratches called striations. Glaciers also pluck a rock from the bedrock, lifting chunks and carrying them along. When glaciers retreat, they leave behind this glacially transported material, including erratics, large boulders that have been carried far from their original location and deposited in areas with completely different rock types. Glacial erosion has carved some of Earth's most dramatic landscapes. Mountain valleys that once held glaciers typically have a U-shaped profile, with steep, straight walls and flat floors, unlike the V-shaped profile of river-carved valleys. Fjords, the deep, narrow inlets found in Norway, Alaska, New Zealand, and other high-latitude coastlines, are glacially carved valleys that were later flooded by the sea when the glaciers melted and sea level rose. During ice ages, when glaciers covered much of North America and Europe, glacial erosion reshaped vast areas. The Great Lakes were carved by glaciers. The smooth, rounded bedrock surfaces of the Canadian Shield, visible across much of eastern Canada, were scraped smooth by ice sheets kilometres thick. The fjords and islands of Scandinavia, British Columbia, and southern Chile are all products of glacial erosion. Gravity itself is an agent of erosion through mass wasting, the downslope movement of rock and soil. This includes landslides, where large masses of rock slide down slopes, often triggered by earthquakes, heavy rain, or undercutting of slopes by rivers or waves. It includes slumps, where a mass of soil or rock rotates as it slides down slope. It includes creep, the very slow, barely perceptible downslope movement of soil, so slow it's measured in millimeters per year, but cumulatively significant over long periods. Avalanches, both snow avalanches and rock avalanches, are rapid forms of mass wasting. They can move at tremendous speeds, carrying rock, soil sensor, ice, and snow downslope and depositing it at the base of the slope as a jumbled mass. Weathering and erosion work together. Weathering weakens and breaks up rock, making it available for erosion. Erosion removes the weathered material, exposing fresh rock to weathering. The cycle continues as long as there's land above sea level exposed to the atmosphere. But here's something calming about weathering and erosion. They're slow. Even in the most rapidly eroding landscapes, the land surface lowers by only millimeters per year on average. Mountain ranges take millions of years to erode away. The processes that created the Appalachian Mountains happened about 300 million years ago. The mountains have been eroding ever since, worn down from heights that may have rivaled the modern Himalayas to their current modest elevations. And yet, they're still here, still identifiable as mountains. This slowness means that landscapes change gradually, imperceptibly on human timescales. The mountain you climb today looks the same as it did to your grandparents, and it will look the same to your grandchildren. The changes happen, but so slowly that they're invisible to human perception, and yet those changes are real and ongoing. Every rainstorm, every freeze-thaw cycle, every windstorm carries away tiny amounts of rock and soil. Streams are cutting their valleys deeper. Mountains are being lowered grain by grain. The landscape is being reshaped, slowly, patiently, by forces that have been at work for billions of years. Weathering and erosion are also part of the rock cycle. The sediment produced by weathering and carried away by erosion doesn't disappear. It's deposited somewhere, in valleys, on floodplains, in deltas, on the ocean floor. There it accumulates, layer upon layer, eventually being lithified into sedimentary rock. That sedimentary rock may later be uplifted by tectonic forces, exposed at the surface and subjected to weathering and erosion again, completing the cycle. Soil, the loose material at Earth's surface that supports plant life, forms through weathering. It's a mixture of mineral particles, organic matter, water and air. The mineral particles come from weathered bedrock. The organic matter comes from decaying plants and animals. Soil formation is slow. It can take hundreds or thousands of years for just a few centimeters of soil to form. And yet, given enough time, solid rock is transformed into the rich, productive soil that allows forests and grasslands to thrive. As you rest tonight, think about the patient work of weathering and erosion. Think about rain and wind, ice and chemistry, all working together to break down mountains and carry them to the sea. Think about how this process has been reshaping Earth's surface for as long as land has existed, creating new landforms, new soil, new possibilities. There's something deeply peaceful about understanding that even mountains are temporary, that even the most solid-seeming landscapes are slowly changing, following natural processes that have repeated countless times over the planet's long history. Nothing is permanent. Everything is in motion, even if that motion is too slow to see. And in that motion, in that slow transformation of rock into soil, of mountains into plains, there's a kind of gentleness, a reminder that nature works at its own pace, unhurried, patient, following patterns written into the physical laws of the universe. Rest in this knowledge. Rest knowing that the landscapes around you, seemingly eternal, are actually in slow, graceful motion, always changing, always flowing toward new forms, just as the planet has been doing for billions of years and will continue to do for billions more. Earth's surface is not flat or... It rises into mountains and plunges into valleys. It forms plains and plateaus, canyons and caves, islands and coastlines. These landforms, each with their own distinctive shapes and histories, tell stories about the forces that created them. Mountains are perhaps the most dramatic landforms, rising high above their surroundings, often snow-capped, always inspiring awe. But mountains form in different ways and have different characteristics depending on how they formed. Fold mountains are the most common type. They form when tectonic plates collide and the crust between them is compressed and buckled, folding like a wrinkled rug. The Himalayas are fold mountains, still growing as India continues to push into Asia. The Appalachians and the European Alps are also fold mountains, though they formed from collisions that happened hundreds of millions of years ago and have since been worn down by erosion. Fault block mountains form when blocks of crust are uplifted along faults, fractures in the crust where rock on one side has moved relative to rock on the other side. The Sierra Nevada in California is a fault block mountain range, tilted to the west with a steep eastern escarpment marking the fault. The Basin and Range province in Nevada and Utah is characterized by numerous parallel fault block ranges separated by basins. Volcanic mountains are built by repeated eruptions that pile up lava and volcanic material. They can form in isolation, like Mount Kilimanjaro in Africa, or Mount Fuji in Japan, or in chains, like the Cascade Range or the Andes. Volcanic mountains tend to have distinctive conical shapes, though shield volcanoes like those in Hawaii have gentler slopes. Dome mountains form when magma pushes up the overlying rock layers without erupting, creating a bulge or dome at the surface. Eventually, erosion removes the overlying rock, exposing the hardened magma as a mountain core. The Black Hills of South Dakota are a dome mountain range. Mountains don't last forever. Soon as they're uplifted, erosion begins wearing them down. Water, ice, and gravity work to reduce mountains to plains. The rate of erosion depends on climate, rock type, and the steepness of the slopes. Young mountains like the Himalayas are steep and jagged because erosion hasn't had much time to smooth them. Old mountains like the Appalachians are lower and more rounded because they've been eroding for hundreds of millions of years. Valleys are the low areas between mountains and hills. River valleys form through erosion as flowing water cuts into the land. Mountain valleys carved by streams have a characteristic V-shape, with a narrow floor and steep sides that angle down to meet at the valley bottom. Over time, as the river continues to cut downward and erosion widens the valley, it may develop a flatter floor and gentler slopes. Glacial valleys have a distinctive U-shape with steep, nearly vertical walls and a wide, flat floor. Glaciers are much more effective at erosion than rivers, especially at gouging and deepening valleys. When glaciers melt, they leave behind these U-shaped valleys, often with steep waterfalls where tributary valleys, carved by smaller glaciers, hang high above the main valley floor. Rift valleys form when the crust is pulled apart, usually by tectonic forces. The East African Rift is a prominent example, a vast depression where Africa is slowly splitting apart. Eventually, in perhaps 10 million years, the eastern part of Africa may break away completely, and the rift will be flooded by the ocean, creating a new sea. Canyons are deep, steep-walled valleys carved by rivers, usually in arid or semi-arid regions where there's enough water to erode but not enough to develop wide valleys. The Grand Canyon is the most famous example, but there are countless others. Canyons form because the river cuts down faster than erosion can widen the valley, often because the rock is resistant to weathering or because the climate is dry. Plateaus are large, flat areas at high elevation. They can form when horizontal rock layers are uplifted, without much folding or faulting, maintaining their flat-lying nature. The Colorado Plateau, which includes the Grand Canyon and many other spectacular landforms, is a vast area of nearly horizontal sedimentary rock layers that has been uplifted thousands of feet above sea level. Rivers cutting through the plateau have created deep canyons, but between the canyons, the original flat surface is preserved. Plains are large, flat areas at low elevation. Coastal plains extend from the coast inland and are often formed from sediment deposited by rivers or by sea level changes. Interior plains may be the eroded remnants of ancient mountains like the Great Plains of North America, which lie east of the Rocky Mountains and were formed partly from sediment eroded from the mountains and partly from ancient seabed that was uplifted. Deltas form where rivers meet the ocean or a lake. The river slows down, losing energy, and deposits the sediment it's been carrying. Over time, this sediment builds up, extending the land outward into the water body. The Mississippi River Delta, the Nile Delta, and the Ganges Delta are massive features, each covering thousands of square kilometers and providing rich agricultural land formed from river-deposited sediment. Coastlines are constantly changing, shaped by waves, tides, and currents. Waves erode rock, creating cliffs, sea caves, and arches. The eroded material is transported along the coast by longshore currents and deposited to form beaches and sandbars. In some places, erosion is dominant, with cliffs being undercut and collapsing into the sea. In other places, deposition is dominant, with sediment building up to form beaches, barrier islands, and spits. Islands are landforms surrounded by water. They can form in many ways. Volcanic islands form from underwater volcanoes that build up until they rise above sea level. Oceanic islands like Hawaii, Iceland, and the Galapagos are volcanic. Continental islands like Great Britain or Madagascar are pieces of continental crust that have been separated from the mainland by rising sea level or tectonic activity. Coral islands, or atolls, form on volcanic islands in tropical waters. Corals build reefs around the island. As the volcanic island slowly subsides over millions of years, the coral continues to grow upward, maintaining itself near sea level. Eventually, the volcanic island may sink completely beneath the surface, leaving only a ring of coral reef with the lagoon in the middle. Many of the islands in the Pacific are atolls. Caves are natural underground chambers or passages, usually formed in limestone through chemical weathering. As slightly acidic water seeps through cracks in the limestone, it dissolves the rock, gradually enlarging the openings. Over time, this can create extensive cave systems with multiple chambers and passages. Caves are often decorated with speleothems, mineral deposits formed when water dripping or flowing through the cave deposits dissolved minerals. Stalactites hang from the ceiling, stalagmites rise from the floor, and columns form when stalactites and stalagmites meet and fuse. Karst landscapes develop in areas of limestone bedrock where chemical weathering has created not just caves but also sinkholes, disappearing streams, and springs. The landscape surface in karst areas is often pitted with sinkholes, depressions that form when the roof of a cave collapses or when surface soil is washed into a cave below. Water that would normally flow across the surface disappears into the ground through sinkholes, flowing through the cave system before emerging at springs, often kilometers away. Sand dunes are landforms created by wind deposition. They form in deserts and along beaches, anywhere there's loose sand and wind to move it. Dunes come in various shapes: crescent-shaped Barchan dunes, long linear Siemt dunes, star dunes with multiple arms, each shape reflecting the local wind patterns. The largest sand dunes, in places like the Sahara or the Namib Desert, can be several hundred meters high. Understanding landforms helps us read Earth's history. The shape of a valley tells us whether it was carved by a river or a glacier. The arrangement of mountain ranges tells us about past tectonic collisions. The presence of beaches high above current sea level tells us that sea level was once higher, or that the land has been uplifted. The sediments in a river delta record the history of the river and its drainage basin, with each layer representing a different flood event or period of deposition. Landforms are temporary features, at least in geological time. Mountains that seem eternal are slowly being worn down. Valleys are being deepened. Coastlines are shifting. Islands are subsiding, eroding, or growing. But these changes happen slowly enough that the landscapes we know remain recognizable across many human generations. There's something peaceful about landforms, about the way they shape the world we experience. They provide variety to the landscape, create ecosystems, influence weather patterns, and offer places of beauty and solitude. They remind us that Earth is not a uniform sphere, but a complex, varied planet where forces in the interior push upward and forces at the surface wear downward, creating an ever-changing but slowly changing terrain. Tonight, as you rest, picture the landforms around you. Picture how they formed, the forces that shaped them, the time it took for them to reach their current state. Picture mountains rising, growing grain by grain through tectonic uplift, then being worn down grain by weathering and erosion. Picture rivers carving their valleys over millions of years, cutting deeper with each flood. Picture glaciers advancing and retreating, sculpting the landscape with each pass. These landforms are the visible expression of geological processes, the surface manifestation of forces operating in Earth's interior and at its surface. They're physical records of the planet's history, if we learn to read them. And they're still changing, still being shaped, still following the same patterns that have created and destroyed countless landforms over the billions of years that Earth has existed. Rest in the knowledge that the land around you has a story. A long, slow story written in rock and soil, in slopes and valleys, in the shapes that water and ice and wind and time have carved into the surface of the planet. Within layers of sedimentary rock lie windows to the past, preserved remains and traces of life from millions of years ago. These are fossils, and they tell us about organisms that lived long before humans existed, about ancient environments, about how life has changed and evolved over Earth's long history. Fossils form when organisms are buried rapidly, usually in sediment, before they can decay completely. Most fossils form in water environments, in lake bottoms or on the ocean floor, where sediment regularly accumulates. When an organism dies and sinks, sediment covers it. If burial is rapid enough, the soft tissues may decay, but hard parts like shells, bones, and teeth can be preserved. Over time, more sediment accumulates on top, burying the remains deeper. The weight of overlying sediment compresses the layers below, squeezing out water. Minerals dissolved in groundwater percolating through the sediment can replace the original material of the shell or bone, atom by atom, or fill in the tiny pores and spaces, hardening and preserving the structure. This process, called permineralization, can preserve incredible detail, even the cellular structure of wood or bone. Not all fossils are remains. Some are traces, evidence of an organism's activity. Footprints left in mud that later hardened into rock. Burrows where creatures dug into ancient seafloors. Fossilized dung called coprolites. Even the impressions of leaves or feathers can be preserved, showing the shape and structure of organisms even when no actual tissue remains. Amber, fossilized tree resin sometimes contains insects or small animals that were trapped when the resin was still sticky. These fossils preserve not just hard parts but entire organisms, including soft tissues, in exquisite detail. Baltic amber, from pine trees that grew 40 to 50 million years ago, has preserved thousands of insect specimens, providing a snapshot of ancient forest ecosystems. Fossils tell us what lived when. The principle of fossil succession, recognized in the early 1800s, states that fossils appear in rock layers in a consistent order. Fossils of the same species are found in rocks of the same age worldwide. Fossils of different species appear in rocks of different ages. This allows geologists to correlate rock layers from different locations and to establish the relative ages of rocks based on their fossil content. Certain fossils, called index fossils, are particularly useful for dating rocks. Index fossils are from organisms that lived for a relatively short time, geologically speaking, were widespread geographically, and are easily recognized. The presence of a particular index fossil indicates that the rock layer was deposited during the time when that organism lived. Trilobites, extinct marine arthropods, are excellent index fossils for Paleozoic rocks. Ammonites, extinct cephalopods related to squids and nautiluses, are index fossils for Mesozoic rocks. The fossil record shows how life has changed over time. The oldest fossils, from rocks about 3.5 billion years old, are simple, single-celled organisms, bacteria and archaea. For most of Earth's history, life remained single-celled and microscopic. Complex, multicellular life didn't appear until about 600 million years ago, when the first animals evolved in the oceans. These early animals, soft-bodied creatures that left only faint impressions, are found in rocks from the Ediacaran period. Shortly after, about 541 million years ago, there was a sudden explosion of diversity, the Cambrian explosion, when most major animal groups appeared in the fossil record in a relatively short time. Trilobites, brachiopods, early mollusks, and many other groups appeared, most with hard shells or skeletons that fossilized well. Life remained in the oceans for millions of years. Plants didn't colonize land until about 470 million years ago, starting with simple mosses and liverworts. Animals followed, with arthropods like scorpions and millipedes among the first to venture onto land about 430 million years ago. Fish evolved in the oceans and diversified. Some developed lungs and fleshy fins, adaptations for living in shallow, oxygen-poor waters. These lobe-finned fish were the ancestors of tetrapods, four-legged vertebrates. About 375 million years ago, some of these fish-like tetrapods began to spend time on land. Fossils like Tiktaalik show the transition, with features of both fish and tetrapods, fish with a neck, wrists, and primitive fingers. Amphibians evolved from these early tetrapods, still tied to water for reproduction, but able to live on land as adults. Reptiles evolved from amphibians, developing eggs with shells and waterproof skins that allowed them to live away from water permanently. This happened about 320 million years ago. For millions of years, reptiles diversified into many forms. Some returned to the sea, evolving into ichthyosaurs, plesiosaurs, and mosasaurs, marine reptiles that look superficially like fish or dolphins but are actually air-breathing reptiles. Some took to the air like pterosaurs, flying reptiles with wings made of skin stretched over an elongated finger. But the most famous reptiles are dinosaurs. Dinosaurs first appeared about 230 million years ago and dominated terrestrial ecosystems for the next 165 million years. They ranged from tiny chicken-sized creatures to the largest animals ever to walk on land like Argentinosaurus, estimated to have weighed 70 to 100 tons. Some were herbivores feeding on plants. Others were carnivores, predators that hunted other dinosaurs. Birds are dinosaurs, or more precisely the descendants of small theropod dinosaurs. The first birds, like Archaeopteryx, show clear transitional features, feathers and wings like birds but teeth and a long bony tail like dinosaurs. Modern birds are the only surviving lineage of dinosaurs. When we say dinosaurs went extinct 66 million years ago, we mean non-avian dinosaurs. Birds survived and flourished. The extinction 66 million years ago, at the boundary between the Cretaceous and Paleogene periods, was one of 5 major mass extinctions in Earth's history. This one was likely caused by an asteroid impact, a rock about 10 kilometers across that struck what is now the Yucatan Peninsula in Mexico. The impact created a crater 180 kilometers wide and threw vast amounts of dust and debris into the atmosphere, blocking sunlight and causing global cooling. Plants died, food chains collapsed, and many groups of organisms went extinct, including all non-avian dinosaurs, pterosaurs, and most marine reptiles. But mass extinctions are followed by radiations, periods when surviving groups diversify to fill ecological roles left vacant by extinction. After the dinosaurs disappeared, mammals, which had existed alongside dinosaurs for over 150 million years but had remained small and mostly nocturnal, diversified rapidly. Within 10 million years, mammals had evolved into forms ranging from tiny shrews to large herbivores, from insect eaters to predators, from tree dwellers to swimmers. Primates evolved about 55 million years ago, initially small tree-dwelling animals. Over millions of years, primates diversified. Some lineages led to modern lemurs, monkeys, and apes. The human lineage, hominins, split from the lineage leading to chimpanzees about 6 to 7 million years ago. The fossil record of human evolution is fragmentary but growing, with fossils showing the gradual acquisition of traits like upright walking, larger brains, and tool use. Modern humans, Homo sapiens, appeared about 300,000 years ago in Africa. We're a very recent arrival in the grand sweep of Earth's history, existing for only about 0.007% of the planet's 4.54 billion year history. If Earth's history were compressed into 24 hours, humans would appear in the last minute before midnight. Fossils are precious and rare. Most organisms don't fossilize. They decay, are eaten, or are destroyed before burial. Even if an organism is buried, it might be destroyed by later geological processes, metamorphism, or erosion. The fossil record is biased toward organisms with hard parts, toward marine environments where burial is common, toward common species rather than rare ones. Despite these limitations, fossils provide our best record of past life, revealing a history far more ancient and diverse than anyone imagined before fossils were systematically studied. Fossils also preserve evidence of ancient environments. Marine fossils in rock that's now on mountaintops tell us that those areas were once underwater. Fossil leaves and pollen tell us about ancient climates. Fossils of tropical plants in Antarctica tell us that the continent was once warm and forested. Fossils of whales in inland deserts tell us that those areas were once at the coast or underwater. As you rest tonight, think about the incomprehensible spans of time preserved in fossils, about organisms that lived hundreds of millions of years ago, about whole worlds that existed, flourished and disappeared long before humans evolved. Think about trilobites swimming in ancient seas, about giant ferns in carboniferous swamps, about dinosaurs walking across floodplains that are now deserts. The rocks beneath you may contain fossils, traces of life from Earth's deep past. Even if you can't see them, they're there in many places, preserved in subcool stone, waiting to be discovered. Each one is a message from the past, a fragment of an ancient organism that somehow escaped decay and destruction, that somehow made it through millions of years of geological processes to reach us. There's something humbling about fossils, about realizing how ancient life is, how many forms it has taken, how many species have come and gone. We're part of this history, one species among millions, a recent branch on the tree of life that has been growing for billions of years. And there's something peaceful too about understanding that life has survived so much: ice ages and warm periods, asteroid impacts and volcanic catastrophes, changing continents and changing climates. Life persists, adapts, evolves. The details change, but the underlying process continues, unbroken, from the first cells billions of years ago to the present day. A chain of life stretching across deep time. Rest well, knowing that you're part of this ancient lineage, that the genetic material in your cells can be traced back through countless generations to the very beginning of life on Earth, that you carry within you the accumulated history of billions of years of evolution, of survival, of adaptation to an ever-changing planet. The rocks and minerals beneath our feet are more than just geological curiosities. They're resources that humans have used for millennia, from stone tools and pottery to metals and gemstones to the fossil fuels that power modern civilization. Understanding how these resources form helps us appreciate both their value and their finite nature. Minerals are naturally occurring, inorganic crystalline substances with definite chemical compositions. Some minerals are valuable because of their properties. Quartz crystals, with their regular hexagonal structure and hardness, are used in electronics and watches. Gypsum, a soft mineral, is ground into powder to make plaster and drywall. Halite, rock salt, is the salt we eat and use to de-ice roads. Calcite makes cement and lime. Some minerals are ores, rocks that contain economically recoverable amounts of metal. Hematite and magnetite are iron ores. Chalcopyrite is a copper ore. Galena is lead ore. Sphalerite is zinc ore. These minerals form in specific environments, often where hot, mineral-rich fluids have circulated through cracks in rocks. depositing metals as they cool or react with surrounding rock. Many metal deposits form at plate boundaries. At mid-ocean ridges, seawater circulates through hot volcanic rock, dissolving metals and then depositing them when the water cools or reacts with different rocks. These deposits, called volcanogenic massive sulfides, are rich in copper, zinc, and other metals. On land, similar processes occur in areas with active volcanism or where seawater has penetrated into hot crust. At subduction zones, fluids released from the descending plate can carry metals upward into the overlying crust. These fluids may form ore deposits in several ways. They may replace existing minerals in rocks with ore minerals. They may deposit minerals in veins, cracks in rock filled with minerals precipitated from fluids. They may form porphyry deposits, large, low-grade ore bodies that form around cooling magma chambers. Copper, gold, silver, molybdenum, and other metals are often found in porphyry deposits. The largest copper mines in the world, like those in Chile and the southwestern United States, are porphyry copper deposits. These deposits form over millions of years as magma intrudes into the crust, and mineral-rich fluids circulate around and above the cooling magma body. Gold and silver often form in hydrothermal veins, where hot fluids circulating through cracks deposit the metals as the fluids cool or react with surrounding rocks. The gold rushes that shaped much of the American West in the 1800s were based on these vein deposits, with prospectors following veins of gold-bearing quartz through the mountains. Diamonds form under conditions of extreme pressure and temperature, more than 140 to 190 kilometers deep in the mantle. At these depths, carbon atoms are squeezed into the dense crystal structure of diamond. Diamonds are brought to the surface rapidly in volcanic eruptions called kimberlite pipes, narrow volcanic vents that blast through the crust carrying fragments of mantle rock, including any diamonds present. If the ascent weren't rapid, diamonds would transform back into graphite, the more stable form of carbon at low pressures. Diamond-bearing kimberlite pipes are rare and scattered. Most are found in old, stable parts of continents, in areas called cratons. South Africa, Canada, Russia, and Australia have significant diamond deposits. Prospecting for diamonds involves looking for kimberlite pipes, then determining if they contain enough diamonds to be economically viable. Gemstones form in various ways. Some, like diamonds, form deep in the mantle. Others form in pegmatites, very coarse-grained igneous rocks that crystallize from the last water-rich portions of magma, allowing crystals to grow very large. Beryl, including emeralds and aquamarine, forms in pegmatites. Topaz and tourmaline also form in pegmatites. Sapphires and rubies, varieties of the mineral corundum, form in metamorphic rocks under high temperature and pressure. The famous star sapphires, with the six-rayed star pattern, get their stars from tiny needle-like inclusions of another mineral aligned along the crystal structure of the corundum. Opals form in a completely different way, when silica-rich water percolates through rock and deposits silica in cracks or cavities. As water evaporates, the silica forms tiny spheres that stack in regular arrays, creating the play of colour that makes opals valuable. Most opals come from Australia, where ancient volcanic rocks have been weathered, and silica has been deposited in the resulting cavities. Coal, oil, and natural gas, collectively called fossil fuels, form from organic material buried and transformed over millions of years. Coal forms from plant material, mostly from trees and ferns that accumulated in swamps and was buried before it could decay completely. Over time, as the organic material was buried deeper and subjected to heat and pressure, it transformed, first into peat, then into lignite or brown coal, then into bituminous coal, and finally into anthracite, the hardest and most carbon-rich form of coal. Most coal deposits formed during the Carboniferous period, about 360 to 300 million years ago, when vast swamp forests covered much of the land and plant material accumulated in thick layers. These ancient swamps are now coal seams, layers of coal sometimes several meters thick, buried beneath other sedimentary rocks. Oil and natural gas form from marine organisms, mostly microscopic plankton, that died and sank to the ocean floor. When buried under sediment in oxygen-poor conditions, the organic material didn't decay completely. Instead, over millions of years, heat and pressure transformed it into hydrocarbons, long-chain molecules made of hydrogen and carbon. This process, called catagenesis, breaks down large, complex organic molecules into simpler ones. The hydrocarbons migrate upward through porous rocks, eventually accumulating in reservoir rocks, porous rocks like sandstone or fractured limestone where oil and gas can accumulate. A non-porous cap rock above the reservoir prevents further upward migration, trapping the oil and gas. These geologic traps can contain enormous volumes of oil and gas, accumulated over millions of years. Finding oil and gas requires understanding the geology of sedimentary basins, areas where thick sequences of sedimentary rocks have accumulated. Geologists look for the right combination of source rocks where organic material was originally deposited, or reservoir rocks where oil and gas can accumulate, cap rocks that trap the hydrocarbons, and structures, folds or faults that concentrate the oil and gas into recoverable deposits. The Gulf of Mexico, the North Sea, the Persian Gulf and the Western Siberian Basin are some of the world's largest oil and gas producing regions. Each has a complex geological history that created the conditions for hydrocarbon formation and accumulation. Water itself is a resource, and geology controls where water is found and how it moves through the ground. Groundwater is water stored in the pore spaces and fractures of rocks and sediment underground. It fills the spaces between grains in sandstone, the cracks in fractured rocks, the solution cavities in limestone. The upper surface of the zone where all pores are filled with water is called the water table. Below the water table, rocks are saturated with water. Above it, in the unsaturated zone, pores contain both air and water. The depth to the water table varies depending on climate, rock type and topography, from a few meters in some areas to hundreds of meters in others. Aquifers are layers of rock or the sediment that hold significant amounts of water and allow water to flow through them easily. Sandstone, fractured limestone and layers of gravel and sand are good aquifers. Wells drilled into aquifers can extract water for drinking, irrigation and industry. Some aquifers are recharged rapidly by rainfall infiltrating from the surface. Others, especially in arid regions, were filled with water thousands of years ago when the climate was wetter and are not being recharged significantly today. These fossil aquifers are being depleted by pumping, raising concerns about long-term water availability. The geological materials we use, from stone for building to metals for manufacturing to fossil fuels for energy, are all products of geological processes operating over long time scales. They form through specific sequences of events that took millions of years. This means they're finite resources. Once extracted and used, they can't be replaced on human timescales. Understanding the geology behind these resources helps us appreciate their value and the importance of using them wisely. It also helps us understand where to look for new deposits and how to extract resources with minimal environmental impact. As you rest tonight, consider that the materials around you, the metal in your lamp, the coal or oil that might have generated your electricity, The gems in jewellery, the stone in buildings, all have deep geological histories, each one formed through specific processes under specific conditions, often millions of years ago. Each one carries a story if we know how to read it. There's something grounding about understanding that the resources we use came from Earth, formed through natural processes, accumulated over unimaginable spans of time. It connects us to the planet, reminds us that we're dependent on geological processes for much of what we use daily. And it reminds us that these resources are precious, the product of millions of years of Earth's work. Using them wisely, conserving them where possible, and seeking renewable alternatives where we can are not just environmental imperatives, but ways of respecting the deep time and natural processes that created them. If you could watch Earth from space for 1 billion years, fast forwarding through time at a rate where 1 million years passes in a second, you would see something remarkable. The planet would seem almost alive. Continents drifting like clouds, mountains rising and eroding away, oceans opening and closing, ice sheets advancing and retreating, a constant, slow dance of change. But at human timescales, geological change is mostly imperceptible. The ground beneath us seems solid, permanent, unchanging. We build structures that we expect to last for centuries. We think of landscapes as eternal. Mountains are metaphors for permanence, and yet nothing is permanent, not on geological timescales. Everything is in motion, everything is changing, just so slowly that we can't perceive it directly. Continents are moving right now, drifting across the surface at rates of a few centimeters per year. That's about as fast as fingernails grow. At this rate, you won't notice the motion in a lifetime. Even in 1,000 years, continents will have moved only a few dozen meters. But over millions of years, these tiny motions add up. Continents that are now separated by oceans will collide. Oceans that exist today will close. New oceans will open where continents are splitting apart. Mountains are rising in some places, primarily where tectonic plates are colliding. The Himalayas continue to rise as India pushes into Asia, gaining a few millimeters in height each year. Over millions of years, this slow uplift has created the highest mountains on Earth. But even as mountains rise, erosion wears them down. The two processes happen simultaneously. Uplift working to increase elevation, while erosion works to decrease it. In young mountain ranges like the Himalayas, uplift is currently winning. The mountains are getting higher, but eventually the tectonic forces driving uplift will weaken or cease, and erosion will dominate. The mountains will begin to shrink, lowering gradually until they're reduced to rolling hills or plains. This has happened to countless mountain ranges throughout Earth's history. The Appalachians were once as tall as the Himalayas. Now they're modest, rounded, worn down by hundreds of millions of years of erosion. Rivers are cutting their valleys deeper, slowly but steadily. Every time it rains, every time the river floods, it carries away a little more rock and sediment, deepening its valley infinitesimally. The Colorado River has been carving the Grand Canyon for about 6 million years, cutting through rock at an average rate of about 0.15 millimeters per year. At this rate, it would take 6,600 years to cut through 1 meter of rock. And yet, given enough time, the Viverware has carved a canyon more than 1.6 kilometers deep. Glaciers are melting and advancing, responding to changes in climate. During ice ages, glaciers expand, covering vast areas with thick ice sheets. During warm periods, glaciers retreat, melting back to their source regions in mountains or polar areas. We're currently in a warm period, though not at peak warmth yet. Ice sheets still cover Antarctica and Greenland, but most of North America and Europe, which were under ice sheets as recently as 15,000 years ago, are now ice-free. But climate changes, and ice sheets respond, though slowly. The ice sheets that covered much of the northern hemisphere during the last ice age took tens of thousands of years to grow, and tens of thousands of years to melt. The same slow response time means that ice sheets today will continue to respond to current climate changes for centuries or millennia, even if climate stabilizes. Sea level is changing, rising as ice sheets melt and ocean water warms and expands, falling when water is locked up in ice sheets during ice ages. Over the past 20,000 years, since the peak of the last ice age, sea level has risen about 120 meters as the great ice sheets melted. That's an average of 6 millimeters per year, though the rate varied, with periods of rapid rise and periods of slower rise. Currently, sea level is rising about 3 millimeters per year due to warming ocean water and melting ice. This may not sound like much, but over decades and centuries it adds up. Coastal areas that are above water today may be submerged in the future. Islands are at risk. Some coral atolls in the Pacific, with elevations of only a few meters above current sea level, may be uninhabitable within this century. But even this change, dramatic as it is for coastal communities, is gradual on human timescales. Sea level doesn't rise suddenly. It rises millimeter by millimeter, year by year, a slow encroachment that gives time for observation and adaptation, though not always time for prevention. Volcanoes erupt periodically, some frequently, others only every few thousand or million years. Between eruptions, magma accumulates beneath the volcano in chambers, slowly filling, waiting for the pressure to build to the point where it can break through to the surface. Some volcanoes, like those in Hawaii, erupt frequently enough that eruptions seem almost routine. Others, like Yellowstone, erupt so infrequently that the time between eruptions is measured in hundreds of thousands of years. Yellowstone's caldera-forming eruptions, the largest volcanic events the region experiences, have occurred roughly every 600,000 to 800,000 years over the past 2 million years. The most recent was 640,000 years ago. This doesn't mean another is imminent. Geological cycles aren't that regular, but it does mean that such an eruption is possible at some point in the future. Earthquakes release stress that has been building in Earth's crust as tectonic plates move. The plates don't move smoothly. Friction along plate boundaries causes stress to accumulate. When the stress exceeds the strength of the rock breaks, releasing energy as seismic waves and earthquake. Then the cycle begins again, stress accumulating until the next earthquake. Major earthquakes on a given fault segment might occur every few hundred to few thousand years. The San Andreas Fault, for example, produces major earthquakes in different segments at different times. Some segments rupture every few hundred years, others less frequently. Between earthquakes, the stress builds quietly, invisibly, a slow deformation of rock that will eventually be released suddenly. Even rock, which seems perfectly solid and unchanging, is slowly deforming. Under the pressures and temperatures found deep in the crust, rock can flow like a very, very viscous fluid. This flow is so slow that it's measured in millimeters per year at most, often much less. But over millions of years, this flow allows tectonic plates to move, mountain ranges to rise, and rock to be folded and deformed without breaking. This is ductile deformation, the slow, continuous deformation of rock without fracturing. Is different from the brittle deformation that causes earthquakes, where rock breaks suddenly. Whether rock deforms in a brittle or ductile way depends on temperature, pressure, rock type, and how fast stress is applied. deep in the crust, where it's hot, rock deforms ductilely. Near the surface, where it's cooler, rock deforms brittly, breaking in earthquakes. Understanding this slow, patient behavior of Earth helps put things in perspective. The changes that seem so dramatic to us, earthquakes, volcanic eruptions, landslides, are just brief punctuation marks in a much longer, slower story. Most geological change happens gradually, incrementally, over spans of time so long that humans can't perceive it directly. This can be comforting. It means the world is stable on human timescales, even though it's changing on geological timescales. The mountains aren't going to disappear overnight. Continents aren't going to suddenly split apart. The changes happen, but slowly, at a pace that allows ecosystems and species to adapt, most of the time. It also means that trying to understand geology requires thinking in different time frames than we're used to. We need to imagine processes playing out over millions of years, changes so gradual that no human has ever witnessed them, but that, cumulatively, have reshaped the entire planet countless times. There's a kind of peace in this understanding, in recognizing that the Earth operates on its own timescale, following its own rhythms, unhurried and patient. The planet has been here for 4.54 billion years. It will be here for billions more, slowly changing, slowly cycling its materials, slowly following the patterns written into physics and chemistry. We're visitors on this timescale, brief sparks of consciousness in a much longer story, but we're also part of the story made of the same atoms, following the same physical laws, embedded in the same cycles that have shaped the planet since its formation. Think about the patterns that repeat throughout geological time. The supercontinent cycle, where continents gather together into a single landmass, then break apart and disperse, only to eventually come back together again. This has happened at least 3 times in the past 2 billion years, and probably many more times before that. Each cycle takes approximately 400 to 600 million years to complete. Think about the rock cycle, where igneous rock weathers into sediment, sediment becomes sedimentary rock. Sedimentary rock is metamorphosed, and metamorphic rock may melt to become magma that solidifies into new igneous rock. This cycle has been operating continuously since Earth's surface cooled enough to have solid rock. Every rock on Earth has been through this cycle multiple times. Think about the water sink or water evaporating from oceans, condensing into clouds, falling as rain or snow, flowing back to the oceans through rivers and groundwater. This cycle has been operating for billions of years, since Earth first had liquid water on its surface. The same water molecules have been cycling through this system over and over, being part of clouds and glaciers and rivers and oceans and living things countless times. These cycles are nested within each other, interconnected, operating at different timescales, but all part of the larger system that is Earth. The tectonic cycle operates over hundreds of millions of years. The rock cycle can take millions to hundreds of millions of years. The water cycle operates on timescales from days to millions of years depending on where the water is. The carbon cycle, which moves carbon between rocks, oceans, atmosphere and living things, operates on timescales from years to hundreds of millions of years. Understanding these cycles, understanding their timescales, gives us perspective on change. Change is not threatening when you understand it as part of a cycle, as part of a pattern that has repeated countless times before and will repeat countless times again. The planet has its rhythms, its patterns, its ways of moving material and energy through its systems. We can learn to recognize these patterns, to appreciate them, to find comfort in their regularity and inevitability. Tonight, as you drift towards sleep, remember that Earth is moving beneath you, slowly, imperceptibly but really. Tectonic plates are drifting, mountains are rising and eroding, rivers are cutting deeper, ice is melting or accumulating, magma is rising toward future eruptions, stress is building toward future earthquakes, rock is folding and deforming deep underground. All of this is happening right now, this moment as you lie still. The slow dance continues as it always has, as it always will, following patterns older than life itself, patterns that will persist long after all current life is extinct and new forms have evolved to replace it. There is something deeply calming about this perspective, about understanding that change is constant but gradual, that the Earth is always moving but never hurrying, that the processes shaping the planet follow timeless patterns that have repeated billions of times and will repeat billions more. Rest in this knowledge. Rest in the slow, patient rhythms of the planet. Rest knowing that the ground beneath you is part of an ancient dance, slowly changing, slowly moving, but for now, solid enough, still enough, permanent enough to hold you as you sleep. The earth beneath your feet is older, more complex and more dynamic than it might seem. It's layered like an onion, each layer with its own properties, its own temperatures, its own mysteries. It's covered with the thin skin of crust that breaks into pieces, plates that drift across the surface, colliding and separating, building mountains and opening oceans. It's made of rock that transforms, cycling from one form to another, melting and solidifying, weathering, eroding, being buried and uplifted in an endless dance of creation and destruction. It's dotted with volcanoes that bring material from the depths to the surface, with earthquakes that suddenly release stress built up over centuries, with glaciers that carve valleys and shape coastlines. It's home to layers upon layers of history, preserved in rock and fossil, telling stories of ancient seas and forests, of creatures long extinct, of climates very different from today's. It's rich in resources, metals and minerals, fossil fuels and gemstones, all products of specific geological processes operating over millions of years. And it's still changing, still evolving, still following the same physical and chemical laws that have governed it since its formation. Mountains are rising and eroding, continents are drifting, oceans are opening and closing. Climate is changing, life is adapting, the cycle continues as it has for billions of years. Understanding these geological processes gives us perspective. It reminds us how old the Earth is, how slowly most changes happen, how temporary even mountains are on long enough timescales. It connects us to the planet, helps us appreciate that we're made of Earth's materials, that we depend on its processes, that we're part of its story. It also fills us with wonder. The Earth is not a simple sphere of rock. It's a complex, dynamic system with interactions between different layers, different processes, different timescales, all producing the rich, varied world we see around us. Learning about geology is learning to read this complexity, to see the stories written in stone, to understand how the landscape came to be. Tonight, you've journeyed through deep time, from Earth's formation billions of years ago to the present day. You've descended into the planet's layers, from the thin crusts to the hot, dense core. You've watched continents drift and collide. You've seen how rock transforms through the rock cycle. You've witnessed volcanoes erupt and glaciers carve valleys. You've travelled through the fossil record, watching life evolve and diversify. You've learned about the resources Earth provides. And through it all, I hope you found a sense of calm, a recognition that the Earth is ancient and patient, that it operates on timescales far longer than human lifetimes. that the processes shaping it are gradual and largely imperceptible, but real and ongoing. The ground beneath you is solid, stable, supporting you as you rest. But it's also the part of a larger system, always changing, always in motion, part of cycles that have repeated countless times and will repeat countless more. You're connected to this system, made of its materials, subject to its processes, living on its surface, brief but real, temporary but significant. As you drift into sleep, let these thoughts settle into the background. Let the images fade, mountains and valleys, layers and cycles, fossils and minerals. Let the timescales become abstract, billions of years, blending into a sense of deep time beyond human comprehension. What remains is the feeling, the sense of being part of something much larger and older than yourself, of resting on a planet that has been here for so long, that has supported so much life, that continues its slow, patient work whether you're awake or asleep, whether you're thinking about it or not. The Earth will be here tomorrow and the day after, and for billions of days beyond that. Its processes continue, its cycles repeat. It breathes in and out, mountains rising and falling like slow, deep breaths, continents drifting like thoughts moving through a sleeping mind. And you, resting on its surface, are part of this, connected through the atoms in your body, through the air you breathe, through the ground that supports you. You're made of earth, shaped by its history, subject to its laws, part of its ongoing story. Rest well, sleep deeply, let the slow rhythms of the planet carry you into dreams. And if these explorations helped you relax, if they gave you a peaceful way to end your day, consider liking and subscribing to The Sleepy Scholar. It helps others find these gentle journeys through science and wonder, one sleepy soul at a time. Good night.